In this demonstration, we're going to have a look at the way in which you can convert sound waves to electrical signals or electrical transverse waves. In other words, we're able to get an image or a picture of what sound looks like. What we're going to use is the microphone, which is inbuilt in the computer, and computing software, and from that be able to have a look at a number of features of sound. First of all, the difference between a soft sound and a loud sound. Secondly, the difference between a low frequency note, musical note, and a higher frequency musical note. If we have a look at the purpose of this practical, as you can see, the aim of this is to observe the change in amplitude and period of sound waves as their pitch and loudness are changed. When we're talking about the pitch of sound, we're talking about its frequency. Now, the word pitch is something which applies to sound, and it doesn't apply to other waves. So, for example, we don't talk about the pitch of radio waves or the pitch of X-rays. It's the sound that we're listening to. So what we're going to do now is listen to some notes played on the piano. And now we'll listen to 4 different sounds. First of all, a soft sound. Now a loud sound. And a low frequency. And high frequency. And we'll take a closer look at what we've actually got. So here are the 4 pieces of sound that we've been talking about. I've done a little bit of editing to take out some of the sounds that we don't need. What we're going to do is expand these views to get a better picture of what we've got. I'm going to pull this down to begin with. And this first one here, you might remember, is the soft sound. To get a clearer view of the soft sound, I'm just going to click here and expand the x-axis. So you can see there that what we've got is a consistent sound or a regular sound, and its amplitude, I can make this a little bit big if I click here. As you can see, there is round about 0.15. So that's the soft sound. I'll reduce the x-axis and we'll have a look at this louder sound. What I'd ask you to do is just to take a sample of the wave here and make a copy of that into your workbook, just a few waves. Now we'll go to the loud sound, and in order to do this I'll contract the x-axis, and here just somewhere in the middle here have a look at the loud sound. So again, expanding the x-axis. So you can see there the difference between loud and soft. You can see over here a figure of somewhere around 0.045. So what you need to do then is just draw a sample, maybe something like this, those waves like that, to illustrate the difference between loud and soft. I'll reduce the x-axis again to move then to the low frequency sound, and that was this one here. So again, I'll click in the middle here and we'll focus on a couple of waves. Now we've got a regular pattern here, which means it's a musical sound. I'll just make it a bit bigger We're not looking at the amplitude this time. And now if I select, let's say 10 waves, so here, so this would, all right, I've got 10 waves there. And if I have a look at this scale up here, it tells me the time, okay? And down here in the bottom left, you can see the starting time here is 5.648, and the finishing time over here is 5.694 seconds. Now, if we do a subtraction of these two numbers, that will give us the time for 10 vibrations. We'll be able to determine the frequency of that note. Now, that note was a note called A. So that was the lower frequency. So getting the difference between these two numbers gives us a figure of 0.46. So moving on then to the higher frequency. So just focusing on one section of the high frequency, I'll click on this to expand our view and perhaps select a few waves like this and make this a little bit bigger. Okay, so here we've got our high frequency. So again, what I'll do is I'll count out 10 waves. 7, 8, 9, 10. So there are our 10 waves. I'll just check that again. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 full waves. And if we have a look at the times down here or up here, doesn't matter too much. So there we've got a figure of 8.580, and the second figure is 8.603. So we get the difference there, and that will be 0.023. So that's for 10 waves. So for one wave, the period, it's going to be 0.0023. We can compare that time for what we had previously, which was 0.0046, the period for the other one. So that was 1 octave, or twice the frequency of the previous note. That frequency actually was for the musical note A above middle C. So you're now in a position where you can do two things. First of all, draw samples of low frequency and high frequency or high pitch, and you can write in to your workbook the time for 10 vibrations, otherwise known as 0.23, and then the time for one vibration, which of course is 1/10 of that. Then you can work out the reciprocal of that, 1 over that, over the period, over the 0.0023, and find the frequency. Here in the workbook, you need to print out a screen capture or a screen copy of the high frequency to show where the sound that we were looking at started and finished. You'll need that for your prac exam. Now further down here you can see where you fill in the information that I mentioned to you before. So what you'll have to do is just go back in the video, do a screen capture, put that in. You should be able to fill in all of the other information, which is down here. And that, as I said, is how we have been able to work out the frequency of sound using some software, and to have a look at loudness, softness, low pitch, and high pitch.